All right, so 5.3 independence and multiplication rule. Two events are independent if the occurrence of one, magnify that a little more. The occurrence of one event does not affect the other. Two events are dependent if the occurrence of one event does affect the other, or does affect the other. That's an effect. So two events are independent if the occurrence of one event does not affect the other. And then two events are dependent if the occurrence of one event does affect. Keep saying effect, does affect the other. All right, scrolling up. So the next, or the first exercise is independent or not, basically independent or dependent. So A, suppose you flip a coin and roll a die. Are the events obtain a head and roll a die independent? In other words, does flipping a coin have anything to do with rolling a die? Does it affect the probability of one happening? So they are independent. One has nothing to do with the other. All right, any problems with that? So the next one, are the events earned a bachelor's degree and earned more than $100,000 per year independent? All right, no, they are not independent. Even though earning your bachelor's degree does not guarantee you will make $100,000 a year, but it will increase your chances of making $100,000 a year. So they are not independent. All right, any questions? Any questions? Anyone still copying? I'll scroll up. All right. So multiplication rule for independent events. If we want to know the probability of E and F occurring, so remember last section, we were looking at the probability of E or F happening. Now we're looking at the probability of E and F happening. If they're independent, all we're going to do is take those probabilities and multiply them together. All right. I'll probably go back. Are you still copying that? All right, so let's look at this next example. In the game roulette, the wheel has slots numbered 0, 00, and 1 through 36. A metal ball rolls around a wheel until it falls into one of the numbered slots. What is the probability that the ball will land in the slot numbered 17 two times in a row? I'll give you a chance to write that down. All right. So first thing we want to ask ourselves, are these two events independent? So these events are independent. The occurrence of rolling 17 does not affect rolling 17 a second time. So in other words, if you roll 17 the first time, they pick the ball up. It's not like they close the hole of 17 or close extra holes or whatever, or slots. So hitting 17 the first time has nothing to do with hitting 17 the second time. So these are independent events. If these events are independent, that means going back here, that's all we have to do is multiply the probabilities together. So first thing we need to do is establish our sample space. Remember we talked about doing probability last class, establishing the sample space. How many total possible number of outcomes do you have? And it's 38 because we have 1 through 36 and then 0 and 00. So that's 38 numbers altogether. And then 17 is just one number itself. So that's one outcome. And you talk about the event of rolling to 17. There's only one way you can roll a 17. So the probability of rolling a 17 is 1 over 38. All right, so make sure we're okay with that before we go to the next thing. All right, so now we know that the probabilities are independent. So that means we can just take the probability of rolling a 17, and we want to know what's the probability of rolling 17 twice. So we're going to take 1 over 38 multiplied times 1 over 38. That represents the probability of rolling a 17 two times in a row. And that will be 1 over 1444. So pay attention to my math lab. Make sure you answer the correct question correctly. They may want it in fractional form. Other times they may want it in decimal form. Make sure you pay attention to the directions and to what decimal place they would ask you to round it out. All right, any questions? All right. Let's look at the next one. Okay. The probability that a randomly selected 24-year-old male will survive the year is 0.9986 according to the National Vital Statistics Report. What is the probability that 3 randomly selected 24-year-old males will survive the year? What is the probability that the 20 randomly selected 24-year-old males will survive the year? So, okay. First one was 3 randomly selected 24-year-olds, and the second was 20 randomly selected 24-year-olds. So, for anyone who wants to write that down, I'll give you a chance to do so. All right. So checking out what's the probability of first one is what's the probability that 3 randomly selected 24-year-old males will survive the year. So first thing you have to ask yourself, are the events independent? In other words, the fact that one guy survives a year, does that affect the ability of another person surviving the year? And they have nothing to do with each other. So that means that our events are independent. Since they are independent, that means we can just multiply the probabilities together. So the probability that a 24-year-old male will survive is 0.9986. They gave that to us. So now the probability that all three survive, if we chose three men or males, 24-year-old males, randomly, what's the probability that all three survive? So we'll just take 0.9986, multiply to itself 3 times for each individual, the probability that each individual will survive. And that'll be your answer. 0.9958. So you'll have your calculator. You can always raise it to the third power, either cube it or raise it to the third power. Depends on what type of symbolism you have available to you in your calculator. If not, just do it the long way. 0.9986 times 0.9986 times 0.9986. All right. Questions on that? Questions? Now, for the probability that all 20 that you choose survive, then just like we did for 3, we would multiply it times itself 3 times. This time we would multiply it times itself 20 times. So we would raise 0.9986 to the 20th power. And that would be 0.9724. So once again, you want to make sure you have a calculator that you can raise a power to. You don't want to have to type out 0.9986 20 times in order to get the answer. So it depends on what type of calculator you have. Some of them have this button right here, where you have a block, then a block raised to another power. I mean, raise a superscript up. So that means that you can raise it to a power. But, some of them have a button like that, have X with Y up there. So it just depends on what type of calculator you have. If you have any questions about it, then always feel free to ask. All right. Questions on A or B? All right. Scrolling up. Very good. All right. So here it says compute the probability that at least one male out of 1,000 24-year-olds will die during the course of the year if the probability that randomly selected 24-year-old male survives the year is 0.9986. Once again, give you a chance to write that down. All right. So here, notice what we're looking for this time is that at least one male out of the 1,000 will die. So we're not looking for the ones that will survive. We're actually looking for what's the probability that one of them will die. So we're going to use the complement rule because the probability that we have is that the person will survive. 0.9986 is that the 24-year-old will survive. So if we're looking at the probability that out of the 1,000, at least one will die, what we'll do is find the probability that none of them will die. and that's taking that 0.9986 and multiplying it to itself 1,000 times. Then we're going to subtract that from 1. Because remember, the complement is everything else. So this is the probability that all of them will survive. And we want to find out the probability that at least one will die, if not more. Then we would take that probability and subtract it from 1. And that 0.7536 will be the answer. All right, questions on that? Make sure we're good. All right. Any problems before we go to the next thing? Make sure we're good. All right, so yep, that's independent. Next session deals with dependent events or conditional probabilities. So 5.4, conditional probability and the general multiplication rule. All right. So conditional probability is the probability that F occurs given that E has already occurred. So notice the positioning of the letters and the symbolism. You have F/E. So that's the probability that F occurs given that E has already occurred. So you can look at that slash as given. The probability F happens given E has already happened. All right. All right, so here is our conditional probability rule. And once again, this positioning matters. The fact that F is first and E is second matters. So if you're going to calculate the probability that F has occurred, probability that F occurs given that E has already occurred, take the probability of E and F, place it over the probability of E, or if you have the number of E and F, place that over the number of outcomes in event E. All right. So everybody done with that before I go to the whole chart. All right, so here we have this chart, the marital status of males and females 15 years or older in the US, and it is in millions. That's what the green asterisk is for, it says it's in millions. So we have never married, married, widowed, divorced, and separated, and then totals. Oh, here we go. So that's this column right here. On top, we have male, female, and totals, and then all of our numbers, corresponding numbers. All right. Am I still copying the table? All right, so it says compute the probability that a randomly selected individual has never married, given the individual is male. That's going to be the key, to our setup. And then B, compute the probability that a randomly selected individual is male, given the individual has never married. So I'll let you write that down, then we'll look at how we're going to find this out. All right. So I'm going to call N never married and M male. So the first one we're looking at A. Why is this not going up? There we go. We want to find a probability that the person never married, given the individual is male. So that's going to be N/M, never married, given the individual is male. So we're going to take the number from the chart that would represent those who are never married and male, and the number of males that we have. So we go back to the chart. So never married and male, 41.6. And then the total number of males, 122.5. So that's what we did here. And that's our probability. Any questions on that one? All right, so for B, compute the probability that the randomly selected individual is male, given that the individual never married. So this time they flipped it. The first one was never married, given that the person is male. This time we're looking at male, given that the person was never married. So going back to our chart. So here we already saw never married and male. And then the other one was the total was never married. All the people that are never married, according to this table. So that'll be 41.6 over the 78.5. And that's our answer. As always, once you convert it to a decimal, make sure you pay attention to what my math lab is asking of you. Decimal place wise, round to 3 decimal places, round to 2, round to 4. Make sure you watching that. All right. Questions? Any questions? Make sure we're okay. All right. Let's look at the next one. So suppose that 12.7% of all births are preterm. Also, 0.22% of all births resulted in a preterm baby who weighed 8 pounds, 13 ounces or more. What is the probability that a randomly selected baby weighs 8 pounds, 13 ounces or more, given that the baby is preterm? And then, is this unusual? All right. So I'm going to call W weighs 8 pounds, 13 ounces or more, and then P preterm. Baby that's preterm. So the probability, it told us that the probability that a baby will be preterm is 12.7%. So always, convert your percent to decimal before you start doing calculations with them. And then the probability that a baby is preterm and weighs 8 pounds, yeah, 13 ounces or more is 0.0022. And so we got that from there as well. All right. So now we want the probability that a baby selected, a random baby selected, would be 8 pounds. I keep wanting to say 18, 8 pounds, 13 ounces or more, given that the baby is preterm. So that's what we have right here. W, given that P has already occurred. So the top is going to be the probability that a baby is preterm and weighs 8 pounds, 13 ounces or more. Bottom is going to be the probability that the baby is preterm. All right, so that's 0.0022 over 0.127. And as a percentage, that would be 1.73%. So remember the last part of that question said, is this unusual or not? So yes, this is unusual because remember our marker was 5%. We said if anything's less than 5% or 0.05, then it would be considered unusual. All right, questions on that? Any problems? Any problems? All right. Can you scroll up? Is everybody good? All right. So the general multiplication rule, probability of E and F occurring, is you take the probability of E and then multiply it times the probability of F, given that E has already occurred. And that's what we explored just a while ago, previous examples. So these events are not independent. You have to explore the idea that one has occurred given that the other one, the one is going to occur given that the other one has occurred. All right. Okay, the probability that a driver who is speeding gets pulled over is 0.8. The probability that a driver gets a ticket, given that he or she is pulled over, is 0.9. What is the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket? All right. So let's look at what we have. I'm going to call T getting a ticket, P being pulled over. Probability of getting pulled over, say it is 0.8. So that's what we got right here. Speeding and getting pulled over is 0.8. Then the probability of getting a ticket given that he or she was pulled over is 0.9. But we wanted to know what's the probability of getting pulled over and getting a ticket. So you take those two probabilities, multiply them together. That 0.8 times a 0.9 would be 0.72. All right. Questions. All right. Let's go to the next one. This might be the last. Yep, this is the last one. All right, so the first part of this, it is studied to determine whether preferences for self are more or less prevalent than preferences for others. Researchers ask individuals to identify the person who is most valuable and likable to you or your favorite other. Of 1,519 individuals surveyed, 42 had chosen themselves. So that's the first part of this. I'll give you a chance to write that down, then we'll scroll up to the actual questions. All right, so first one, suppose we randomly select one out of 1,519 individuals. What is the probability that he or she had chosen self as a favorite other? All right, so our sample space is going to be 15, 19. That's the total number of people that we can choose from. And then out of those 15, 19, we know 42 of them chose self. So the probability of getting someone who chose themselves as their favorite other will be 42 over that 15, 19. So that's just that. That's all they're asking for that first one. What's the probability of choosing somebody who chose 42, who chose themselves as their favorite other? All right, problems with A. Make sure we're okay. All right, B. If two individuals from this group are randomly selected, what is the probability that both chose self? All right. So we know the probability that if we had one person that chose self, the probability of getting that person was 42 over the 1519. Now we want to look at the probability that two people that we chose and that both of them chose self. So the way we'll set it up is that we know the first probability is going to be the one we already had from the first problem, which was A. The chance of choosing one person that chose self would be 42 over that 1519. The second one is going to be the probability of choosing someone who chose self, given that you already found somebody who chose self. All right. So look at how we will manipulate this a little bit. So like I said, the first one is 42 over the 1519. After you chose that person, then there's one person that's taken away from the 42, and that means there's one person that you took out of the 1519. So that's why it's 41 over the 1518. So there's 41 people left that still have chose self out of the group, and then there's 1,518 people left out of the group, as a whole. All right, so make sure it makes sense. So it went down in each category. There were 41 people left because that first time you chose one, you chose somebody who chose self. And then in that bottom number, that's how many people are left in all. All right, so multiply those together, and that'll give you 0.000748. All right, looking at C, compute the probability of randomly selecting two individuals from this group who selected self, assuming independence. So in other words, we're assuming that when you choose one, it's not going to affect the group at all. And so if that's the case, whenever it says independence, that means that the probability of one event does not affect the probability of another event. So 42 over that 1519, multiply it times itself twice, and that will be your probability. All right, questions. Make sure we're good. All right. All right, so that is it for 5.3 and 5.4. All right. Did anybody have any questions on anything? All right, some questions may not be generated till you actually get in there into my math lab, so I understand that. Anybody still copying before I move out the screen? All right, cool. So just give you a heads up as to what's going on. I think we talked about this last class, what was about to happen next. So next class, we'll look at 6.1 and 6.2. But that's all there is for chapter 6. So we'll actually be done with chapter 6. So we should be looking to do test 3. let's see how many days we have left in this class. So that's going to be on the 12th. We got the 14th. We got 7 and 8. Yeah, I don't think we really have time to do what I was looking at doing. May 7th is that last week. Yeah. So the way we're going to be doing this is that each one of your tests will be, done through my math lab, except for your final exam. And then that will be done proctored. So the way we would do our proctored test is that you will come in regular Zoom time. You will enable your cameras and then show your ID. And then you will just take the test. You can use your notes. I won't take your notes away from you or anything like that. But that will probably be our only proctored test. Just looking at the time and trying to give you guys an opportunity to get this work done. All right. So questions on anything. So that this test 3, will be posted in my math lab. So, all right. So if you guys don't have any questions, then you're good to go. Next class, like I said, we'll get into the 6th, and also once again open up the floor for questions, see if anybody had them, and we'll go from there. All right. So you guys have a great weekend. Be safe, and I will see you on Monday.